Okay, in this unit, we're going to talk about language modeling. Language modeling is the problem of modeling the probability distribution over natural language, over English. Shannon was very interested in this problem. How much information in bits is being transmitted when we speak to each other? Now, you may be aware that the hottest thing in the last 3 or 4 months in deep learning is this thing called GPT-3. GPT-3 is this monster language model that's doing all kinds of exciting and interesting things, but it is a language model. So it is the kind of thing that we're going to be talking about now. So language modeling is trained using an instance of our fundamental equation. In this case, it's unconditional. We're sampling sentences of English or blocks of English text or some language, and we're trying to build a model of the probability distribution over sentences. And we're trying to build that model by minimizing the average when we draw sentences from the population of minus log the probability of that sentence. So it's an instance of the fundamental equation. But it should be clear that the probability of a long sentence gets vanishingly small, because every time you generate a word, you're taking there are many possible words, and the probability of a given sentence is vanishingly small. So there's no way to sort of enumerate all the possible sentences. You have to do something else. So let's set up the formal problem. So formally, we're going to assume some finite vocabulary of tokens. Let's think of those as words. These days, people use other kinds of tokens, byte pair encodings, but let's think about words. So the population, the space of sentences, is a probability distribution over strings of words. So we're trying to apply our fundamental equation to model the probability distribution over strings of words. Okay. To make this feasible, we use an autoregressive model. And that word is something you need to remember, autoregressive. So autoregressive means you're predicting each word conditionally on the words that have occurred before it. So you're doing a kind of regression that's modeling the probability distribution of the next word based on the previous words. And this showed up first in linear predictive coding and speech recognition. So auto-regression goes way back. But here we're just, the idea behind an auto-regressive model is that you predict a structured object one element at a time using a probability conditioned on the elements that you've already generated previously. So that's just this equation. The probability of the sequence is the product over all the elements of the probability of that element given the elements that came before it. We can also introduce an end of sequence token. So remember that when we compute entropies, we want a prefix-free code. So an end of sequence token will mark the boundary between sentences, and that lets us know when the output has terminated. So that we can then, if we include the end of sequence token, we get a prefix-free code, and the prefix-free code, we can define a probability distribution over the terminated sentences. We have to, in an auto-regressive model, you have to know when to stop. And so this lets us define a probability distribution over sequences of different lengths. Sentences of different lengths. Okay, I just want to mention a few standard measures of performance. There are 2 different kinds of language model, or at least 2 different kinds. I've talked about language models where you're predicting the next word at each autoregressive step. You can also define language models that are predicting the next character, 1 byte, 1 character at a time. And those language models also work surprisingly well. The 2 forms of models are actually fairly competitive with each other. By standard practice, when you're generating one character at a time, you measure the performance in bits per character. And a typical language model uses 1 bit per character. When you're generating words, 1 word at a time, the standard measure is perplexity. And perplexity is looking at the number of bits per word, except it's a little trickier than that. So if you you generate a bunch of text, you look at the total log probability, you add up all the log probabilities, divide by the number of words, that's giving you a number of bits per word, assuming you're using log base 2. But then the perplexity is 2 to the number of bits per word. So if the distribution was uniform, 2 to the number of bits per word would be the number of possible words if the distribution was uniform. So I said it was 1 bit per character is typical. Perplexities of about 60 were typical until just a few years ago. And then things got crazy. So it also turns out you can calculate the average number of characters per word so that you can translate between perplexity and bits per character. Perplexity can be computed from bits per word. And it turns out that 1 bit per word corresponds to a perplexity of about 55. So the 2 kinds of models are in the same ballpark. As of March this spring, when I looked it up, the state of the art in neural language models yields perplexities of about 10. So they were 60. So language models have dramatically improved. And language models are playing a really fundamental role in many natural language applications these days. And we're going to be talking about that in later units. Thank you.